Здравейте! Добре дошли на втората лекция от поредицата лекции. Този следобед ще имаме удоволствието да чуем първата лекция на професор Попеску-Пампу. Аз ще го представя много неформално. Значи вчера беше един формален следобед, днеска вече почваме в по-работен стил да се движим. Творческият път на професор Пампу започва от Румъния. Неговата майка е французойка, баща му е румънец, но той израства в Румъния до своята 17-годишна възраст. И първото му състезание, голямо състезание, Балканската олимпиада по математика, на която той става златен медалист, а следващата година вече е в отбора на Франция. И там става също златен медалист от Международната олимпиада по математика. След това професор Пампу следва в много известен колеж във Франция, който е специален колеж, който подготвя гимназистите за университета. Ние нямаме такава структура в България, казва се клас препаратуар. И той следва в най-известния такъв във Франция, Люи Льогран. Там са изследвали много известни френски математици, един от които е Галуа, за който всички сте чували. След това професор Пампу завършва Екол Нормал Супериор. Това е най-престижното френско учебно заведение, един от първите в своя клас. И след това започва бурна кариера в областта на математиката, геометрията и топологията. Неговата лекция ще бъде много визуална. Аз искам само да споделя едно лично впечатление от професор Пампу. Преди няколко месеца той ме покани да изнеса доклад в университета на Лил. Посрещна ме на гарата. Това рядко се случва, вече на такова ниво. Идват много още ученици. Добре. Посрещна ме на гарата, беше ранен следобед. Питаме дали съм гладен, аз отговорих, че не съм, което беше груба грешка. Отидохме в един хотел и ми каза: Тони, искам да разбера каква е твоята математическа вселена. За първи път получих такъв въпрос. И след това аз в продължение на 4-5 часа разказвах на професор Пампов какво ме вълнува в математиката. И той следващите 5 часа разказа какво него го вълнува в математиката. И мога да ви кажа по какъв начин се прибрах в моя хотел, едвам ходейки. На другия ден по същия начин щях да изпусна влака, защото той трябваше да ми разкаже много красиво доказателство, което беше намерил на класически резултат в математиката. Това е математик, който живее с математиката, който ще се радва много с вас да си поговори за каквото ви вълнува. Утре професор Пампу ще има среща с ученици в Института по математика и информатика от 10:30. И за да не ви отекчавам повече, давам думата на професор Пампу.
So, thank you very much, Tony. I imagine that what you said was very nice about me, and happy I could not understand. So thank you very much. It's an opportunity for me to discover for the first time Sofia and more Bulgaria, because next week I will be in Plovdiv, and I heard it's a wonderful city, and I'm very curious of that. And of course I'm very honored to be able to speak in such a prestigious place, and also honored to contribute at my scale to the development of relations between France and Bulgaria, and more generally to relations inside Europe at a moment when a lot of people believe that the future can be constructed only by restricting to its own country or village. And I'm a believer that mathematicians who always progressed disregarding countries and looking only at ideas can be a model for other persons. And I'm happy to be able to try to share with you my taste of mathematics and the fact that it makes me every day travel in wonderful landscapes of ideas and shapes. And in particular, I want to explain you today mathematics with a lot of drawings and of shapes. So perhaps it will be a little non-standard, but for me to understand anything means to draw a lot. So let's enter in the realm of drawings. Today we will discuss only one theorem, and we will turn around it and look at it from many different viewpoints. It's a theorem from the 17th century due to Blaise Pascal, and we will see that we will have also different ways to express this theorem, but I will start with a simple one, which is easy to draw with a compass and a ruler. It tells that if we have a hexagon inscribed in a circle, the three intersection points of pairs of opposite edges are aligned. So I think that a lot of you know this theorem, but if you want to draw it, to see what happens, I think each time you draw things for the first time, you have this surprise that you cannot see the theorem because the intersection points are outside the page. So in fact, if you want to illustrate it, you have to be careful, to place carefully the 6 points on the circle. But there is a trick in which you do not have this problem and automatically the points are on your page. You have just to realize that in the statement of the theorem, nobody told you that the hexagon should be convex. So in particular, you can draw it in this way. So this is a way to draw a hexagon. So hexagon inscribed in the circle means that first we have 6 points on the circle, but second we have to choose a well-defined order of the points in order to draw the edges. And you can draw the edges such that the three intersection points of pairs of opposite edges lie inside the circle. And here we can have a first exercise. If you want to see in how many ways you can join them such that the three intersection points lie in the circle, you will see that you get only this configuration. And this configuration means what? That in fact you divided the 6 points into two groups of neighboring threes. So 3 here are neighbors. These are neighbors, and now they are like face to face, and the rule is to join each point to those which are not in face. So this one is not joined to the one just in face of it, so to the two other ones. This one is not joined to this one, is joined to the two other ones. And in this way, it's not obviously clear visually what are opposite edges. So then we can say that because we have a hexagon, if we choose one edge, then we drop the next two and we choose the third one. So if you do this with this blue edge here, we drop next two and we choose this one. And in order to make this visually clear at one glance, I used colors. So you see the pairs of opposite edges are those of the same color here, blue and green and yellow. And then the three intersection points of the theorem are these 3 ones. And then it's a visual check. You can take a ruler and pass it through, and you see that those points are aligned. So this is the content of Pascal's theorem. So you see that already just in order to get a nice drawing, you have to think a lot about the configuration and the way to draw it. And in fact, my experience is that you can understand a lot by not just sketching and then forgetting it, but being very careful about the drawings you make. And this obliges you to explore a lot of theory, in fact, in order to make drawings. But now, let's come back to a convex hexagon, and let's take a kind of extreme case where all the opposite edges are parallel. And this is what happens, for instance, for regular hexagons. Then the theorem seems to be empty, because it speaks about the intersection points of opposite edges, and here we do not have such points. So, what does this mean? That the statement is incorrect, that we should say when the opposite edges meet, then those points are aligned. So it means that the statement is less nice, it's longer. And in mathematics, the length of a statement is a kind of measure of niceness. We prefer short statements, and here it means that in order to have a correct statement, it should be longer. But there is, in fact, a solution to this. And the solution will be brought by thinking in perspective. And in fact, it's not a matter of thinking, it's a matter of viewing. I think all of you saw avenues like this. This is taken in Lille, where I live. I think not all avenues have golden parallelepipeds like this. This is now in Lille because there is a cultural semester which is called Fiesta, and this is one of the decorations of the city for this Fiesta semester. But for me it's good because you see here, this allows you to see many parallel lines. And visually you see that all those parallel lines seem to meet at one point. So this is a concrete lesson of our way of perceiving the world, is that if we look in perspective of things, we see that parallel lines meet. So our problem is that an intersection point of parallel lines was lacking, is solved by our vision. So let's explore a little this phenomenon. Here I show you a second photograph. I took this year in Valladolid in Spain, the center of Spain. And here, this is a palace of the end of the 15th century, and you can see two systems of parallel lines. One on the right here, all these ones are parallel, and you see if by imagination you follow these lines, you see that they meet at some point here. And here you have a second system of parallel lines, and they meet at another point there. And now you have 2 points, and you know that 2 points generate a line. And so there is some line here, and we could ask what's the meaning of that line. And it turns out that if you look at any other system of parallel lines which are parallel to the soil, well, they seem to intersect at a point on this line. And to have it in your drawing, it's enough to have these 2 systems of parallel lines, because of the first axiom of Euclid, who says that a line is determined by 2 points. You do not need more. So please look here, it's a situation where we have to invoke the first axiom of geometry. So I said that our problem was about hexagons inscribed in circles. And we were looking at a hexagon where opposite edges were parallel, and then we dealt with this problem of parallelism of lines. But let's think now about the circle. If we look at it in perspective, what we see is such an elongated shape. So I am sure you know the name of this shape, but I invite you not to know it, and just to look at it, not as mathematicians, but as anybody in the street, and to contemplate the fact that this explanation, you can do it to anybody in the street. And this is very precious, because we have a kind of distance to be filled all the time between those who like mathematics and those who are afraid about mathematics, and it's precious to know which important pieces of mathematics can be explained without a lot of theory. So explaining that a round circle appears like something elongated, you can show this to everybody. So now I spoke about lines and about circles. This is a photograph I took this year in Madrid, in the Retiro garden. Let us pass to a picture I took yesterday in Sofia. So here I combined both parallel lines and circles seen in perspective. And you can see also here parallel lines which could be either here common tangents to all these circles or the lines of the centers of these circles. And also you have tangents here and also there. And you see also that the circles, when they are farther and farther, you see the elongation increases. So we do not see the same shape for the circles which are near us and those which are far. And you see that we can perceive this immediately, a priori, without any theory. The need of theory appears if we want to understand better the way the shapes deform. But just see how here we are in front of mathematical questions. So now that we saw intuitively what happens in perspective with circles and lines, let us go back to our regular hexagon and look at it in perspective. But before that, I want to show you that to understand carefully that trick, we need to become building theory. And here, the first who built theory were the painters in the 15th century. And one of the most important ones from this viewpoint is Piero della Francesca, who wrote a treatise of perspective. So the ways, the rules for drawing things in perspective. And here I show you 2 pages of this treatise. This is a manuscript. So here, see, he took a pencil and he drew all of this. And here is something about drawing columns. And here you see the column vertically and here laterally. And then on the right page, you see, in fact, the bottom of the column drawn in perspective, obliquely here. But how? So the theoretical problem was indeed how to draw correctly this. When what? When a viewpoint is fixed. So I don't know if it's very clear, but perhaps you see here that, for you it's very clear. For my screen it's not so clear, but you see a lot of lines. So this represents here the eye of the artist. We have to choose where to place ourselves. And he understood that in order to make correctly this drawing on the right, one has to represent the viewpoint in 2 projections. In this projection here, the soil projection, so the viewpoint appears here, you see laterally with respect to the column, and also vertically. This gives the height. And then one has to report information from these 2 drawings here. And that's why you see a lot of points which are reported here. And if you see here, he reported a lot of points which are joined with segments. And in this treatise, it's very interesting because he does the same thing with heads of persons. Because I wanted to speak with you about polygons, I did not put a head. But he does the same very carefully with a view from above of a head. Imagine that here you have the head seen from above, a lateral one. And then here you have a representation which is oblique of a head and seen from little above. And everything is drawn point by point, and then points are joined by successive segments. And if enough points are drawn, then you get the illusion of roundness. But if you are looking here, you see that only segments are drawn. And this was systematized at the beginning of the Industrial Revolution by Gaspard Monge in France in the 18th century, and then it began the way of drawing everything for making things in industry. Until my time, we had to study this. Now computers replaced all of this. It was called industrial design, and I suffered a lot with industrial design because one had to be extremely precise in performing all these reports of points. And what I preferred was to think geometrically about it, not to put with precision 80 points on a page. But industrial revolution was done also because of this precision of making drawings of shapes in space, which was applied to everything. And I wanted to show you this. The first time I saw, wow, somebody was already thinking about this in 1470. I was amazed. So now, what happened here? There is no here. So now we get nearer the hexagon. Here you see again a column, but with a hexagonal base here. And it is constructed in the same way as before. So I invite you just to remember that we have a shape we want to construct, and then this shape has to be seen from a point. So there is a point of view, and then we have to draw all the lines joining the point to the object we are wanting to see in perspective. And if we do this now with a regular hexagon, then let us think about our two rules. We said that parallel lines should meet at the horizon. So there is a line at the horizon where all parallel lines meet. So it means that when we take a couple here of opposite edges, because they are parallel, well, they will meet on this horizon here. And these two also, and these two also. So if you look in perspective at a regular hexagon, what you see is in fact a hexagon inscribed not in a circle, because a circle is seen in perspective, but in this elongated shape, where the opposite edges meet in aligned points. And they are aligned just because they are on the horizon. And my conjecture is that Pascal discovered his statement, the statement of the theorem, in this way. And then he could try to prove it. But you see here there is a very important point about the way we write mathematics. The absolute model of writing mathematics, which is still nowadays is a kind of absolute model, is Euclid. And in fact, Euclid said absolutely nothing about the way he wrote his treatise of elements of geometry. And that's why his treatise was read mostly by everybody, not only mathematicians, but also philosophers, as a model of logic. But before putting things in a logical order, one has to discover the statements. And discovery is not done by logic. Imagination is fundamental, like in painting. So that's why I showed you things done by painters, because I believe we are, in our spirit, really their brothers and sisters. So here, my conjecture is that Pascal discovered his statement like this. He said, let's look at a regular hexagon in perspective. You can look at it from many different viewpoints, from higher or lower, from farther or not, and you saw that the elongated shape changes. But all the time you get the opposite edges meeting in three aligned points. So for me, this is the most credible reconstruction I have of the way he could think first about this statement. But you see that in this statement, the statement is not about a circle, but about these elongated shapes. So let us look at a little at them. So now I said you surely know what they are. So what's the name of this elongated shape here? An ellipse. So let us speak about ellipses. But speaking about ellipses, we will discover that if we think about them from the viewpoint of optics and of perspective, we cannot avoid speaking also about other curves. And you will discover that if you think enough about an object, say you are interested for a precise reason, industrial application to biology, to something, if you think carefully, you will see that you are obliged to think also about something else. And that's why we need researchers. Because to understand a precise object for a precise reason, the experience of centuries and millennia showed us that cannot be done without understanding the context. And the context is not given by the person who asks you the question. It's only careful analysis and dream and work with a lot of examples, which at the moment gives you all the interacting characters of the theater. So let us see. Here I show you something which is a little posterior to Piero della Francesca. It comes from a wonderful treatise of geometry written at the end of his life by Albrecht Dürer, whom I find one of the most fantastic drawers of all times and all civilizations. And it's, I said written, but written and drawn. It's full of drawings, and it's in fact a treatise of geometry for artists, in which he explains to artists how to draw a lot of shapes. And one of the lessons is, well, how to draw with precision an object we are looking at. So you see here, I told you that there is a viewpoint. Here, this is the eye of the artist. Here, you see, it's not the eye of the artist, it's a point in the wall. And one imagines that one looks at the object from here. You cannot put your eye there because of the wall. But then by uniting with a chord successively this point with many different points of your object, here a lute, and seeing where it intersects a plane, this is a plane here of the drawing, the point is staying, look here at the operation, you need two persons. One which fixes an extremity of your chord, and which also opens the plane of the drawing. Then here, with some instrument, a point is fixed. Then this person takes out the chord, and then he closes this plane. And then the person who is drawing is putting a point there. And that's why you see a lot of points. And when you see a lot of points, where you see there is no freedom of the artist. This is mechanical. This is precisely what computers can do much better than us. At the end, the object pops up. A little like in quantum mechanics, where you don't know in which order the points appear, but they appear. And when you have enough of them, the object is there. Here, it's exactly the same. It's not important to put them following this line. You can mark some points at the beginning on your object and then to put them in any order. At the end, you will get the object popping up on the screen. So this is a mechanical way. I spent some time on it to make you feel all the efforts which were done to understand the phenomenon and to perform it, to get realistic representations. And I hope that you see also that this drawing is not done in this way. This gets from all the experience of drawing of Dürer. Okay? But here he made a lot of pedagogical effort. For me, this is one of the most wonderful illustrations of what is good pedagogy. You see, you can explain a lot of things with just this drawing. So let us fix again this viewpoint and look more theoretically at the fact that we look at an object from it. Then, here we said we wanted to look at a circle. So if you look at a circle from this viewpoint, you take all the visual rays joining the viewpoint to the circle. And then you get a cone. Or say here you see it's a double cone. We have to look at the complete lines through it. Complete lines through it, it's not completely clear because you look at me, I look at you, but I don't look at the same time behind. So I leave this as an exercise to understand why, when you are thinking about these perspective things, we need to double the cone. So to take this surface in space. You see, it's a surface which has here a special point, in which it pinches in some way, which is our viewpoint. In other places, imagine that this double cone is done in paper. And imagine that you put your hand on it. You will feel that it is smooth everywhere, except it at the vertex. Those places where you cannot go and find that the object is smooth are called singular points. So the viewpoint, which allows you to look at the world, is a singular point of the cone of light which is directed towards the object of your inquiry. And now, remember that the artist wants to represent the reality on some screen. And there you have a freedom. This is a fundamental freedom of the artist, which is just the position of the screen. So the screen, geometrically, is a plane. So we have the problem of intersecting this double cone with a plane. And I illustrated this with 3 planes, which all of them pass through the same line in space. This plane intersects it on a closed curve here. And now you have to imagine that you move the plane around this line. And you see that arrives a moment when, after turning, you get a plane which is parallel to one of the rays in the code, which is called the generator of the code. So if you imagine this movement, you see that here you get closed curves, but which get more and more elongated. The point here goes here and escapes at infinity precisely when you get the parallelism of the plane here with this line. So then you get a curve which is not closed anymore, which is the second one. And then if you turn a little more, then you see that the plane intersects here in a curve with the same qualitative behavior as here, but also intersects the other half code. So the full intersection is made of two pieces. And this is already something paradoxical, and I attract your attention, this you have to say to your friends who are not mathematicians, that here we have one curve. For a mathematician, there is one curve, but for everybody else in the street, here you have two curves. But we say it's one, and we have one word for this one curve, which is a hyperbola. So here you see why ellipses, parabolas, and hyperbolas are to be thought together. Because they give us all the possible ways to intersect the cone of view towards an object if we want to represent the object on a screen. And if what you want to represent is a circle, then qualitatively you have three possible curves, which are ellipses, parabolas, and hyperbolas. This, seen from this viewpoint, which makes them a single family, are called conic sections because we are sectioning a cone. So please keep these words in your mind. From now on, when you see conic sections, you have to think about this picture and you say, it's either an ellipse, a parabola, or a hyperbola. So let us go back to Pascal's theorem. If we put in perspective the first version of Pascal's theorem, what we get now is the circle is replaced by a conic section, because we said we look at it and then we view a conic section. And I hope I convinced you that we can view it in all the three types of conic sections. By such a projection, if you have three aligned points on a plane, their projections are still aligned. And as I told you, a circle is projected to a conic section. So in perspective, the statement of Pascal's theorem becomes, given a hexagon inscribed in a conic section, the three intersection points of pairs of opposite edges are aligned. And they are always aligned because we keep the first lesson that such a statement, we should look at it in perspective. So there is always a line at infinity. And this line at infinity, which was perceived by the artists as the line of horizon of a flat Earth, is the line at infinity of Bernard Tessier's talk this morning. It's the same. This morning you saw how you manage it algebraically. Here I tried to show you how you can manage it visually. So are there questions about this putting in perspective? No? So let's continue. Now I want, before getting to the core of my talk, I would like to show you some applications of Pascal's theorem to concrete graphical representations. We already spoke about the beginning of geometry, which is that 2 points determine a line. And in fact, if now after the lines, which are particular curves, we speak about conic sections, and we saw that the conic sections, from the viewpoint of perspectives, are the curves of the family of the circle. If we are saying that everything should be put in perspectives, then circles disappear. What remains is the world of conic sections. We could ask if there is a statement analogous to that for lines. how many points determine a conic section? And it turns out that 5 points determine a conic section. For lines, we needed 2 points without exception. In fact, there is an exception that we need to have 2 different points. If you mark twice the same point, that does not determine a line. Here, there is a more complicated exception. You have to take any 5 points, but you have to ask them not to lie in threes on a line. So not to have aligned triples. And then the statement is that such 5 tuples of points determine a unique conic section. And I want to convince you of this graphically. Something you can really see completely with a ruler on a paper. And for this, the clue is Pascal's theorem. So also pay attention, for the moment I did not prove Pascal's theorem. I want to make you feel how it can be used. I will discuss, in fact, in the sequel 2 proofs of very different nature. And in fact, I'm sure you saw also others. And those which I chose today, I chose them such that I bet are different of what you already saw. But on the internet, if you search for proofs of Pascal's theorems, you can discover a lot of them. Today, I want to show you some proofs which can be extended to much more general ways of thinking. And this is important. Perhaps you know that there are some theorems where mathematicians spent a lot of time to find new proofs. This is not because of a competition, they want to have just a new proof which is better than others. It's because they were thinking in general at much more general phenomena, and the theorem dealing about an object was a kind of baby example from which they hoped to reach something much more general. Exactly like here, the movement where we passed from circles to all conic sections. And the proof which uses in a fundamental way the fact that we have a circle is not good from this viewpoint, because we would like to have a proof which works for all conic sections at once. So this is a kind of things which can push researchers to try to find new proofs, hoping that a new proof will allow better to generalizations to the context which interests them. So what's interesting to ask if somebody tells you about a new proof of something is what inquiry guided that research. In perspective, they were looking in which direction? Because in general, new proofs are directed by ways of looking towards infinity, towards the horizon. And this is very important. So let me go back here. Let me convince you that these 5 points here determine a unique conic section. You think here visually that it will be what? An ellipse, a parabola, or a hyperbola? So you have to pay attention. Yes, indeed it's an ellipse, but it's not obvious if you put points here that they will determine an ellipse. They could very well determine a hyperbola. And if you ask, well, do I know initially here why it's an ellipse? What would you say? Why, just given these points, you think that it is an ellipse? A very simple way to say that something won't be an ellipse is to take the convex hull of the points, like this morning. If you give 5 points, it could happen that the convex hull be a quadrilateral and the 5th point be inside it. If you have that, it cannot be an ellipse. It cannot be even a parabola. It must be a hyperbola. But if the convex hull is a pentagon, then you could be in the 3 cases. This means that the points are, in fact, on the same branch of the hyperbola. If you put 5 points on the same branch of a hyperbola, think about it, the convex hull is a pentagon. So the first visual thing to do, because you see immediately the convex hull, is to check this. So here there is more than this. And I leave this as an exercise. So let's see now. In order to be able to show that there is a unique ellipse or conic section containing these points, I will perform a trick. I will show that each time I choose a line passing through one of the points, I know what is the second point of intersection of the line with the conic section. So coming back here to what we saw, again I have a problem. Pay attention, if you look at lines intersecting these curves, you see that all the time you intersect in exactly 2 points, or if you have tangency 1, or no point here or here. So if you have a line which you know passes through a point of the curve, then it passes through a second one. And what I will show you is that this second point of intersection is in fact determined by these ones. So what do? You take your ruler, you say, well, I will choose these points among the 5 ones, and I draw it in this way. Why did I draw only a half line? Because visually I made like you. I imagine that here I have some ellipse. So I see that I should get an intersection point somewhere here. And my problem is to show that this point is well defined. So now what do? After this first line is determined, I choose an order of the point in order to draw a hexagon. So I have to choose this will be a first edge of the hexagon, and then a second one, and I chose first, second, third, fourth, fifth, and I don't know the 6th point, so that's why I have only 5 edges. But 5 edges are enough to have already 2 pairs of opposite edges. So to see them, again I used my 3 colors. So yellow, and I jump onto yellow. And then green, I jump onto green. So I get here 2 intersection points, which I called 1 and 2. So now Pascal's theorem tells me that the line joining them passes through the 3rd one. But the 3rd one is an intersection point of the remaining color here, which is the blue. So I have to take the intersection point of this Pascal line with the blue edge, and that's how I get the 3rd point here of my construction. Here the numbering is the numbering of the steps of my analysis of the problem. So now that I have this point, I know it's a point of intersection of the 2 blue edges. So the remaining blue edge, I know that it has to pass through this point. So I join it to it, and it intersects here my initial line in this point, which is the 5th one. So I passed here from 3 to 5 because the 4th object was not a point but a line. It's this line joining this point with the 3rd Pascal point. And that's how this is the 5th point of my intersection, and then I know that this is on the conic. So you see, it is determined by the 5 ones. All the construction is how mathematicians call this is canonical. It does not involve choices, it's God-given. And that's how I get this point. And I do this for every line passing through this, and that's how all the points of the conic section are determined on all the lines passing through this point. You will understand this and find this beautiful only if you draw this. So I invite you once at home to really do this for different ways of placing the 5 points. And again, here you saw that I made here a special way of joining them in order not to have points outside my page. So each time you want to use Pascal's theorem, you will see you have this problem. You will have to make drawings which are far from convex in order to have all the points you need on your page. And this you can only discover by experiment. So that's why I invite you to draw. So this was my first application of Pascal's theorem. It's not my application. This was in books of geometry in the 19th century. Everybody learned that in that period. Now I show you a second one. Well, I told you that there is a unique conic section passing through 5 points. So imagine that these are the 5 points. You have, here I drew this conic section, but now you discovered its uniqueness. And there is a tangent to it here. And what I want to show you is that Pascal's theorem allows you to draw this tangent with a ruler, only knowing the 5 points. So the 5 points and the ruler allow you to draw the tangent without having the ellipse. Here you can check visually that this seems to be the tangent. So the clue to this is to pass to the limit. I think that all of you studied limits, but in analysis. And I show you here a context where limits popped up from geometrical problems. And this is true historically. This is one of the sources of problems of limits. Is to take a general statement, here dealing with 6 points on a conic, and what we will do is to collapse 2 neighboring points. So we fix one, and the second one we will move it on our conic section till at the limit it coincides with the other one. So I told you that if you take twice the same point, that does not determine a line. That's the first approximation. If you think better, you discover that in fact, if you take twice the same point on a curve, and there is a precise way to say mathematically that you take them coinciding, but they don't coincide completely. They coincide, and in fact they lie on a precise curve. They determine a line which is a tangent to the curve at that point. And this was in fact discovered algebraically by Fermat. And it's one of the sources of what is called differential calculus, or the first way you discover differential calculus is the study of derivatives. So here, let's do this. I chose on the left 6 points on a conic. I fix 5 of them, and I make move just this one here. And the arrow shows you how it moves towards this one. And then I took here a precise way of drawing a hexagon. It's not my initial one. You see that here 2 of the opposite edges do not intersect inside the conic. And I represented also here the Pascal line. And I am asking what happens with this line at the limit. So if I move 3 points and all the time they are aligned, it means that at the limit I get again 3 aligned points. And what we are searching is to see what happens with all the segments. Well, all the edges of the hexagon become here edges of a limiting pentagon. Excepted this one, joining the points which get collapsed, which, as I told you, converge to the tangent there. And then if you see these 2 opposite edges become this edge of the pentagon and the tangent at this vertex. Do you see in terms of the pentagon what is the relation between this vertex and this edge? We are looking at a vertex of a pentagon and a precise edge of it. Which edge? It's the... Of course, there are lines, so they are defined by polynomials of degree 1. But I'm asking, from the viewpoint of the pentagon, I fix a vertex, and I choose an edge. From the viewpoint of that vertex, which edge do I choose? The opposite, exactly. So you see, I have the vertex, then I start with an edge from it, I count. 1, 2, 3. In a pentagon, if you count from a vertex, first edge, second edge, the third one is the opposite. And you see again, because it's not convex, this does not jump to our eyes. We have to count a little. So you see that the Pascal theorem for pentagons inscribed in conic sections tells you that at each vertex, the intersection point of the tangent and of the opposite edge is aligned with 2 other points, which is you start from an edge passing through it, and then you count 2 and you take another one. So you have again a way to pair the edges and you get 3 points. And the limit Pascal theorem tells you that these 3 are aligned. So what is the rule for drawing the tangent? You just make a pentagon of those 5 points, you get these 2 points of intersection, you draw the line joining them, and you look where it intersects the remaining edge. You get this point here, and now you join it with the opposite vertex of the edge, and that is a tangent. And please do this at home. You will see that given those 5 points, if you do this for each vertex, you will get a circumscribed pentagon here, and you will see much better the shape of your ellipse. If you have only the 5 given points, you see here is not very clear to see. Do you see obviously what is the big axis of the ellipse from these 5 points? How is it? It's like this, more like this. It's not clear. But if you draw the tangents, you will see that your mind tells you much more about the shape of the ellipse. So now I pass to the core of my talk. I was speaking only about a theorem of the 17th century, and then about visual and drawing discoveries of the 15th, 16th century. And then you said, well, what does this have to do with our times? Is there something new to be said about our times? Well, yes. Here is a paper from 2012 by John Conway and Alex Riba. John Conway is a great British mathematician who passed away a few years ago. Alex Riba is still alive, and he's a computer scientist. And here they wrote a very short paper. You see 5 pages. In the Mathematical Intelligencer, Mathematical Intelligencer is part of a few journals for mathematicians, but which are not specialized, in which papers are accepted only if, in spirit, they are understandable by any mathematician from any field. There are few journals like this. In general, the mathematical journals for research are specialized or publish very complicated papers. For instance, there are famous journals like Annals of Mathematics or Invenciones, who are not specialized, but all their papers are extremely sophisticated. They cannot be understood by somebody who does not work in that precise field. The Mathematical Intelligencer has a spirit, like a little, say, American Mathematical Monthly or La Gazette de la Société Mathématique de France in France, and other journals like this. In Spain, Revista de la Real Sociedad Matemática Española. Unhappily, I don't know what's the name in Bulgaria. But those journals, which after a long period of effort of research, you want to read something nice which you will understand easily and make you happy. And what I want to show you is why this paper made me very happy, called the Pascal Mysticum Demystified. So let me enter in it. To understand the paper, you need to have in mind very well this theorem of Pascal. And that's why I spent a lot of time on it. So here, the paper starts with an illustration of Pascal's theorem. And I invite you to see in this illustration what we said before. And then to find something strange in it. You see, please look at the colors and ask yourself, do you understand the way they are put, the colors? For me, the rule was that I used the same color for opposite edges. But if you look here at your hexagon, you will see that there are not 3 colors for the edges, but only 2. So which edges are colored with the same color? The rule is that neighboring edges should have different colors. And this is why, if you follow the edges which have the same color, you see that there are in fact here 2 triangles, a blue triangle and a green triangle. Yeah? So till now we did not use this way of looking at hexagons as a superposition of 2 triangles. But here there is a proof which is famous in the spirit is an adaptation of a proof found in the years 1830 by Plücke, a famous German mathematician. A proof of Pascal's theorem which goes directly to all conic sections. And the proof is algebraic in character. So here let us think about what we see algebraically. First of all, the edges are lines. Being lines, they are defined by polynomial equations of degree 1. ax plus by plus c equals 0. Let me call those polynomials L because they define lines. So the edge AB is defined by a polynomial which I call LAB. So I wrote it in green because you see that they colored the edge AB in green. So this makes the correspondence between the picture and what I write here clear. So the fact that we do not take with the same color neighboring edges translates in the fact that here the indices do not share the same letter. You have AB and CD and EF, and here BC, DE, FA. And now, if you take the product of these three polynomials and you look at that equation, just the green part equal to 0. Well, a product is 0 if and only if one of the factors is 0. But we said that one of the factors is 0 is an edge. So it means that that equation defines exactly the green triangle. And in the same way, the blue equation here defines the blue triangle. And now the trick, and this is a trick really discovered in the years 1820, and the geometers began to play a lot with this trick. This trick is a precise algebraic manifestation of the first axiom of Euclid, which tells that 2 points determine a line. Here we have two curves, the green triangle and the blue triangle. Seen algebraically, they are defined by these two polynomials which are of third degree, because each one here had first degree, and when you multiply, degrees get added. So here we get 3 and 3. So we have two polynomials of third degree. Those are thought as points, and we said that 2 points determine a line. And algebraically, a line is something which can be described by moving one parameter at degree 1. Lines are related fundamentally with degree 1. So that's why here we introduce one parameter, lambda, and we put it with degree 1. And now you see that we get a lot of polynomials of degree 3. One for each value of lambda. And these are polynomials of degree 3, and we say that the curves they define are cubic curves for this reason. So we have a family with one parameter, which is a kind of line in the space of cubic curves. And let's think about those lines. Each point on it represents a cubic. The initial points, which gave birth to everything, were the two triangles. And now, do you imagine what are the shapes of the other ones? It's not so easy. And graphically, it's extremely interesting to draw this. You can say, perhaps one day you don't understand perfectly, but it's a very good theme of reflection to try to understand how those curves fill the plane. But here, we will go directly to the Pascal theorem. We will reason in the following way. Initially, we had 6 points on the conic. Let us fix a 7th one, which I call G. It is not put on the drawing because I did not want to perturb the drawing of the paper of Conway and Riva. You can take any other one. And then you say, do I have a curve in my family here of cubic curves passing through it? That point has two coordinates, A and B. So to pass through it means that this polynomial vanishes at it. So if I put A and B inside this equation, I get an equation in lambda of degree 1. Why 1? Because here the coefficient of lambda is not 0. Why is it not 0? Because this vanishes only on the blue triangle. But each line here intersects the conic in 2 points, which are 2 of the 6 points. And I said that I take a 7th point outside them. So it means that this does not vanish. And an equation of degree 1 has only one solution. So I have one curve in that family passing through it. And now let us contemplate this. I have a cubic curve and a conic, and they have 7 points in common. Why 7? 6, because these two curves here pass through all 6 of them. That's how we took the blue and the green triangle. Both of them pass through the 6 points. And now this curve passes through a 7th one. This morning, Bernard Tessier told you about Bezout's theorem and the fact that for some algebraic geometers, this is the most important theorem of algebraic geometry. I want to make you feel how it can be used, because here it's not an immediate use. Here we found two curves, the conic of degree 2. This is something which has to be shown. It's not immediate from the visual viewpoint. But if you begin to write equations for a conic surface in space and a plane cutting it, you discover that conic sections are of degree 2. And here we have a curve of degree 3. Bezout's theorem tells that they cannot have more than 6 points in common. And here they have 7. So what does this mean? That in fact they have an infinite number of points in common, and this comes from the fact that they have a common irreducible component. But my conic section was irreducible. It's not the union of two other things. So the only solution is that this conic section is part of the cubic. But if a conic section is part of the cubic, the difference of degree is 1. So what remains is a curve of degree 1. But a curve of degree 1 is a line. So it means that this precise member of the family is the union of my conic and a line. So this line will contain the intersection points of the two triangles which are not on the conic. But those intersection points are exactly the points of the conclusion of Pascal's theorem. And that's why they are on the line. And that's why this line is colored with the same color with the conic. Because together they form the red cubic curve, which is this precise member of the family. So in this family of cubics, in fact, almost all the cubics are irreducible. And there are, in fact, 3 special members, the two triangles and the union of the conic with the Pascal line, which are reducible. And in this way, you see that you are thinking about the following. In the space of curve of some degree, I draw a line. That line means that I have a family of curves moving in the plane. And what's the general question? When those curves break into pieces, at some precise moments when accidents occur. And you are thinking about a completely different problem, and you understand that you are led to that problem because of this proof of Pascal's theorem. This is a way a new proof can open new landscapes. And for a researcher, the most important are landscapes of exploration. Something which is huge, so that then you can move there and invite other persons and collaborate with other persons, because there is so much to explore. When we do research, we are not doing like in Olympiads, all the time trying to solve small problems. We are more interested in exploring landscapes. And in fact, it is because I understood that doing research is that after Olympiads, I decided to do research in mathematics, because I was overwhelmed with doing small problems all the time. And I said, no, behind there is this marvel, the universe to explore. And I'm still happy of being able to explore something like this. I'm very happy to be able to share with you, this proof. I find it absolutely fantastic. Also fantastic in the way it uses Bezout's theorem. You say a priori, what does Bezout's theorem has to do with Pascal's theorem? It allows you to see that this line of Pascal and the initial conic are to be thought together as a cubic curve. And cubic curves are fundamental in mathematics. For instance, the proof of Fermat's last theorem is based on the arithmetic of cubic curves. They are called elliptic curves, and elliptic curves are something absolutely central in a lot of branches of mathematics. And they are here. All the other curves, except these which break into smaller pieces, are elliptic curves. So here we are, in fact, touching very important objects. So this was my first proof of Pascal's theorem. I promised that you will see a second one. So now let us enter in the content of the paper of Conway and Reed. What I explain you here was a small paragraph at the beginning of their paper. So the first paragraph of the paper is the following one. The object we call the Pascal mysticum is a remarkable configuration of 95 points and 95 lines derived from 6 points on a conic. In what may be the simplest account yet published, we explain all the incidences of the mysticum in a readily memorable way and provide complete proofs in just a few pages. So what happens here? Till now we were speaking about one hexagon and one line. What's this? 95 points and 95 lines. Derived from 6 points on a conic. Do you see how from 6 points you get 95 points and 95 lines? Well, everything comes from what I said rapidly. That the hexagon is not 6 points. It's 6 points with a cyclic order. You have to say which follows, who follows whom. So let's count that. Say I have my 6 points and I choose. If I call them once and for all A, B, C, D, E, F, I could say, well, I put D, B, F, C, E, and I don't know whom I forgot. So once an order like this is fixed, you can draw the hexagon. But the Pascal line is determined by the hexagon, but you see in what I did more than drawing a hexagon. I chose a first point, and I chose also an order of reading the edges from that point. But the hexagon is the same if I start from another point of it. So in how many ways can I do that choice? To say the list of my points means that I look at a permutation of 6 objects. So I have, in fact, for the first object, 6 choices, and then to be multiplied with 5 for the second, 6 times 5 times 4 times 3 times 2. But now I have to say the initial object is not important. So I have to divide by 6, because I can change the starting point. So dividing by 6, I remain only with 5 times 4 times 3 times 2. And at the end, I have 2 choices of orientation. So I have still to divide by 2. And I get 5 times 4 times 3. This is 20 times 3 is 60. So I get 60 possible hexagons from 6 points on a conic. Each one has a Pascal line. So I see already 60 Pascal lines. But here there are 95. And also some 95 points. What is not obvious how we arrive there. So let's read more. Before this paper, I had no idea about this. If you never heard about this, it's normal. 10 years ago, I never heard about it neither. In the next section, they say, we discuss a remarkable configuration we call the mysticum hexagrammaticum. The permutation notation we use later makes it easy to understand the incidences. We will see that we will have incidences between points and lines. A lot of lines passing through points, and a lot of points which get aligned. And we have found uniform proofs for all the propositions. This permutation notation was used in a proposed book on triangle geometry. After Seiger's death, we were surprised to find that essentially the same notation was already developed in Christine Ladd's 1879 paper. So you see, this happens often. You do something, and then you discover that it was already done. And you say, well, if I knew that, I could have avoided losing time. Well, it was done but completely forgotten. And they could rediscover it because they discovered it anew. Without doing that, they couldn't have recognized that in Christine Ladd's paper. So this is also part of research. If something happens to you, you don't have to be unhappy if you have the same thing. And if you do research in math, it will happen to you. Something which is getting asleep will be born again due to your efforts, because you will find something and now you will be able to recognize that shape in situations when nobody sees that there is something interesting. And this is what happened to them. So let's pass to Christine Ladd's paper, 1879. She was studying with Sylvester in the United States. Sylvester is one of the great British mathematicians of the 19th century, emigrated to the United States. And Christine Ladd did an excellent work in mathematics, but unhappily at that time it was prohibited to women to get PhDs, so she could not have a PhD in mathematics. And afterwards she moved, in fact, to psychology, and she became a specialist of psychology of vision, and she is still known nowadays by that community of researchers. But she started by studying these configurations of points and lines. And the beginning of her paper is, I wish to propose a new notation for the lines and points connected with the Pascal hexagon, to give a brief account of the discoveries of Veronese on the subject and to develop a few additional properties of the figure. We will speak in a moment about Veronese, who is an Italian mathematician. So what she proposed first is a diagram allowing to understand the incidences of all those points and lines. So for the moment, I invite you just to look formally at what you see on this page, and to see that there are 60 Pascal lines. These are the 60 ones I already told you about. And then 20 Cayley-Salmon lines, 15 Steiner-Plücker ones. For the moment, you don't know what they are. But you see that there are also points, Kirchmann points, Steiner points, Salmon points. And you see that there is a symmetry here between 60 and 60, 20 and 20, 15 and 15. And now that she gave names to those points with small letters and capital letters H, G, I, this allows you to interpret this figure. This tells, for instance, that through a point, capital I, it means a Salmon point, pass exactly 4 Cayley-Salmon lines. So I think that even if you look carefully for 5 minutes at this, tomorrow it will be difficult for you to draw this again. So it's not very convenient mnemotechnically. And also to remember these notations, why Kirchmann points are denoted capital H. And what small g has to do with Cayley and Salmon. It's not obvious. But what Conway and Riba say is that what's great is this notation. So you see that she denoted all those lines and points by writing the letters A, B, C, D, E, F in some order. Either all 6 of them, or grouped in packets of 3s, or in packets of 2s. And what they say is that, this is a wonderful permutation notation, which means that this should be seen as a permutation of the set of 6 letters, meaning that A should be exchanged with B, C with D, E with F. And here, A has to be sent to B, which has to be sent to C, which has to be sent to A. And here, D to E, which has to be sent to F, which has to be sent to D. And this is a cyclic permutation of 6 letters. A go to B, to C, to D, to E, to F. So it means that this notation has to be seen dynamically. Till now I spoke about individual points, but now you have to think that they have to be combined in some way. And what's very interesting is that Christine Ladd did not give such a dynamical interpretation, but she thought in another way which led her to this notation. And Conway and Riba thought in a completely different way and arrived from a different perspective to the same notation. This is an important point. This is a sign that probably this notation has a kind of stability. It is important. You cannot avoid it. So let us come now to these discoveries. How to pass from 60 to 95 plus 95. And here is the way they explain this is one paragraph. The 19th century saw a series of grand developments from Pascal's theorem. By taking the same 6 points in different orders, we obtain just 60 Pascal lines, since there are 12 permutations preserving a hexagon. This is what I just explained you. In 1828, Jacob Steiner asserted that these concur in threes in 20 points we call Steiner nodes. In 1829, his great rival Julius Plücker showed that these Steiner nodes lie in fours on 15 Plücker lines. The sequence was continued on 27 June 1849, acceleration, when Thomas Kirchmann announced in a newspaper advertisement that the Pascal lines also concur in threes at 60 Kirchmann nodes. And a month later, when Arthur Cayley showed that these lie in threes on 20 Cayley lines, which also each contain one Steiner node. After one further month, George Salmon closed the system by showing that the Cayley lines meet in fours at 50 Salmon nodes. If you add all this information, you will reach 95 and 95. Oof, how to remember that? You could say, well, why was it so long to discover all of that? Perhaps by drawing carefully, as I did, one can see all of that. Well, in fact, not at all. Here is what one of the heroes of this story, Arthur Cayley, one of the great algebraists and geometers of the 19th century, wrote in 1868 in a paper called A Notation of the Points and Lines in Pascal's Theorem. So you discover that Christine Ladd's notations were in fact part of a great project of research to find good notations which allow to understand all those points and lines. You have to see that that was a completely new problem in math. Till that point, nobody explored incidences between so many points and so many lines. And arrived at such big numbers, things cannot be seen anymore visually. One needs a theory to understand what happened there. And this is very well expressed by Cayley. I have constructed on a very large scale a figure of the 60 Pascalian lines and the 45 Pascalian points, marking them according to the foregoing notation. But the figure is, from its complexity and the inconvenient way in which the points are either crowded together or fly off to a great distance, almost unintelligible. And he did not publish that picture. And in fact, no picture of all of this was published till the 20th century. Let us come back to Conway and Riba's paper, and let's think about the name they gave to this configuration of 95 points and 95 lines. The figure formed by these 95 lines and nodes has in recent years often been called the hexagrammum mysticum, a name that properly only applies to the hexagon of Pascal's theorem. We prefer to interchange the roles of adjective and noun to give the new name mysticum hexagrammaticum, which means mysterious six-lettered construction, abbreviated to mysticum. We will see a little later that mysticum, in this context, comes from Pascal itself, but in a strange way. So one of the main messages of Conway and Riba's paper was this figure, which was a mnemotechnical figure for everything we discussed about these 95 points and 95 lines. So I invite you first to look at it a little and to try to see. What do you see inside? In fact, there is a way to understand everything in this figure, which will make you being able to draw it again in 2 months, for instance. It's indeed something wonderfully mnemotechnical. So you see, they call this the mystic H. So I hope you all see the letter H inside it. And this is, in fact, what you have to draw first, a big capital H. But then you have to enrich your drawing. So, okay, now that you analyzed a little, let us see their explanations. The capital letters in our mystic age provide a handy way to recall which objects are points and which lines. We call the name points nodes because the investigators whose names contain the letter N discovered nodes, whereas those with a non-silent L discovered lines. The silent L in salmon don't pronounce Salmon. Silent L, salmon, quietly reminds us of his independent discovery of the KLE line. The Pascal line of the hexagon ABCDEF will be called L of ABCDEF. You see, L is a line. And you see that L is present in the name Pascal, which tells you that Pascal discovered the line. We can regard the portion ABCDEF of this symbol as representing a permutation, in this case a 6th cycle, in the usual way. It turns out that Kirchmann nodes N of ABCDEF are also conveniently indexed by 6 cycles. In a similar way, Steiner nodes N of ACEBDF and KD lines L of ACEBDF are indexed by products of 2-3 cycles. Please note that here N is present in the name Steiner and L in K. Whereas Plücker, you have a L, so he discovered lines. L of ADBECF and Salmon nodes N of ADBECF are indexed by products of 3-2 cycles. The permutations in these names can be replaced by their inverses, which we alternatively call opposites, so that we can say that permutations index the same object just if they are equal or opposite. I wanted to read this to show you also the preoccupation of mathematicians for the way they express the ideas. For the moment you learned about language, and I think you are in the mode, let's see what others call them, but mathematicians also introduced names. And you see that it is in fact a big trouble to introduce good names such that other people will remember them, and they give sentences which are easy to remember and to reproduce. Let's see now the segments in our figure. The props of our mystic age display all the incidences of the mysticum hexagrammaticum. We use a black prop when the incidence condition is a usual one that the permutations indexing a point and line commute without being equal or opposite. So this is the main advantage of thinking about those symbols as permutations. Because when you have 2 permutations, you can compose them. Perform first this one and then this one, or the opposite. And saying that they commute is that the result is the same. So the rule is that you will join points and lines when the corresponding permutations commute. Very strange. What has permutations, commutativity of permutations to do with Pascal's theorem? Very strange. But this is also, you see, then I feel like in Alice in Wonderland. I feel I am here in a wonderland. What's happening? The white prop, however, indicates that a Pascal line contains a Kirchmann node just when their indexing hexagons are disjoint, have no common edge. I was asked to do a drawing, so this is a good moment for doing the drawing. Say I want to draw the conic section, only the hexagon. So say I have here some 6 points. And say I first choose them in this way. Not to have a common line means, for instance, to do the way of joining them I showed you initially. For instance, between these 3 and these 3. This has to be joined here, this here, and this here. So you fact, they do not commute, but we consider that they have to be joined because they do not have common edges. You see, no segment is both black and blue. And this, from the viewpoint of these two symbols here, may be seen that if you have two neighbors in one of them, they are not neighbors in the other one. A and B are neighbors here, but they are not neighbors in the other. So these are the rules for drawing the edges. These props also name incidence prop positions due to the indicated mathematician. So you have a pun. Prop can be interpreted in two ways, either as a support of something or as a beginning of proposition. The numbers near them count the corresponding incidences. For example, the labels 4 and 3 on the Plücker prop tells us that 4 Steiner nodes lie on each Plücker line and that 3 Plücker lines meet at each Steiner node. The mystic H is a remarkably good mnemonic, they continue. One should read it by columns because the left column contains the 3 earliest discoveries which were made in chronological order by French and German speakers, whereas the right column contains later discoveries by English-speaking writers, again in chronological order. So let me come back to this. And let us try to see all this information packed here. So the props are these black props and the white prop. You see that the white prop connects lines and nodes which are indexed by 6 cycles. So if you said that here the letters are A, B, C, D, E, F, U, V, W, X, I, Z are to be interpreted as unknowns, meaning that you have to put them with this rule. That if you draw this, you do not have common edges. So these are exactly all the allowed ways to connect here L of A, B, C, D, E, F with a node. And this tells you that on such a Pascal line, you have exactly 3 Kirchmann nodes. And the 3 near the Kirchmann node tells that through each Kirchmann node pass exactly 3 Pascal lines. Here you see that you have a Steiner prop between L of A, B, C, D, E, F and N of A, C, E, B, D, E, F. It is because these 2 permutations commute. And in fact they commute for a very good reason, is that in fact if you look at here A, C, E, you are jumping above one point, A, C, E. So in fact, this permutation here is a square of this permutation. And in fact, each time you have a permutation, and if you take a power of that permutation, these 2 objects commute. And for those of you who heard about group theories, if in a group you have an element and the power of that element, they commute. So here there is a very good reason why you have commutativity. Because here you take the second power, and if you look at A, D, B, E, C, F, A and D are here, from the viewpoint of this hexagon, opposite points. And this is in fact the cubes, the cube of this one. But you say, then I should put a prop. Well, I don't put a prop here. Do you see why? Because these objects are lines, and 2 lines always intersect. What may not happen is that a point lies on a line, but 2 lines, when we add the line at infinity, always intersect at one point. So these obvious relations are not added in the figure. Only the non-obvious ones, which are such point lies on such line. So you see here, we start now the chronology of discoveries. We start from Pascal, and we get down here. Then were discovered the Steiner nodes, Plücker lines, Kirchmann nodes, Cayley lines, Salmon nodes. So now you remember very easily in which order things are discovered. You see, moreover, here that lines are connected to nodes, to lines, nodes, lines, nodes. And always lines and nodes are to be connected together. And if you know that the story starts with Pascal, then the fact that here you have an N and that you have to put a German name, if you remember the set of all the names, then to be German you have only these 2 ones. But because you have to put an N, you know that it is Steiner. And then, because you know that the chronology is like this, you know that the first discovery after Pascal is due to Steiner. And then, because here you have to put the other Germanic name, it is Plücker, well, the next one was Plücker. And then, in the same way, you put everything, and you know here everything happens without ambiguity. The only ambiguity is at the end with this silent L here, Salmon. And in this way, you have no problem to remember who discovered what. And if you say, then I have a problem with the numbers to be put here. You see that the numbers decrease from 60, and I explained you how to find this 60 very easily. And then you take divisors, 20 and 15. And this 20, well, 3 times 20 is 60, and 4 times 15 is 60. And if you remember that on such lines, you will never have a 2 on this configuration, because it's not surprising that you have 2 points on a line. All these lines are special because they contain at least 3 points. But some are more special because they contain 4. So if you remember that you have to put only 3s and 4 in the picture, and that here the numbers decrease, well, you know that here you have to put 3 and here 4, and you reconstruct everything. So once you understand all of this, you understand why this is the mnemonic. You can travel in your life now knowing this object. And I don't know if till now you saw such a mathematical production, which is a way to remember more easily a theory. This is one of the reasons I like very much this paper. Very few papers are like this. The majority of mathematicians prove theorems in a very hard way. And you study it, and 1 month later you discover that you completely forgot everything. But happily, from time to time, you have mathematicians who say, it's important for us also to be able to think in a simple way about a complicated world. This complicated world here is made of 95 points and 95 lines. So what is, if we spoke about mnemotechnics, remember that they said they also provide common proofs for all of this. And what is wonderful is that the common proofs are, in fact, all based on, say, perhaps the most basic theorem of projective geometry, which is called Desargues' theorem. And the statement is here. If 2 triangles have a perspector, they have a perspectrix and conversely. What does it mean? Imagine that you have these 2 triangles in the plane, and moreover, their vertices are made in correspondence 2 by 2. And you take these 3 lines. Assume that these 3 lines meet at one point, which they call the perspector of it. It's a point from which, if you look at one triangle, you see exactly the same as the other one. They superimpose. From that viewpoint, you do not see the difference between the 2 triangles. In general, given 2 triangles, you do not have such a point. So, if you have such a point, then automatically the 2 triangles give birth to a special line. You take the intersection points of corresponding edges, and again, like in Pascal's theorem, you get 3 intersection points. The theorem of Desargues is that these 3 points are aligned. So you see the same kind of conclusion as in Pascal's theorem. And conversely, if 2 triangles have a perspectrix, then there is a perspector. So you see that this theorem can be used in proofs in 2 ways. Either to show that triples of lines pass through a same point, or the triples of points are aligned. And all their proofs are like this. So I give you one example. The Kirchmann prop. The Kirchmann prop tells that the Pascal lines, line of 3 permutations here, indexed by 6 cycles disjoint from a 6-cycle pi, meet in a Kirchmann node we call n of pi. So here, I gave you one example. Say that our permutation pi is blue one. So say pi 1 is the black one. I told you that to draw this black hexagon, we have to split the 6 points into 2 packets of 3s, which are face to face. So these 2 here 3 permutations, pi 1, pi 2, pi 3. So that's why you get these 3 Pascal lines. So the Kirchmann probe tells that if you take these Pascal lines, they will meet in a node. And they call that node by the name of the starting permutation pi, which gives birth in this way to the 3 permutation pi 1, pi 2, pi 3. So here is a proof. You see, we have 2 triangles here. The vertices of the triangles are intersection points of some segments determined by the 6 points. For instance, this is the intersection of the line AE and DF, this AC and BF, BD and CE, etc. And now, let us look at the intersection of this line and this line. And they say this intersection, they intersect at the point BE-CD. Why? First of all, look at these 3 points. AE intersected with DF, AC and BF, BE and CD. Where are they aligned? It's not obvious. It's Pascal's theorem. The 6 points are on a conic, and AE and DF, AC and BF, BE and CD are intersection points of opposite edges for one of the hexagons in the configuration. So these are aligned by Pascal's theorem. So to get one of the lines of the configuration, we use once Pascal's theorem. The same for this, the same for this. So we have 3 of the lines given by Pascal's theorem. But if you look at this smaller triangle here, you see BECF, ADBE, BECD, all of them lie on the line BE. So they are aligned for a much simpler reason. So this triangle here gives you alignments which are easy. For the second one, they are not easy. In Desargues' theorem, there is a kind of symmetry between the 2 triangles, but in this application, it is used in an asymmetric way, with 3 uses of Pascal's theorem. So now, we want to prove that these 3 lines intersect at one point. So we will invoke Desargues' theorem. It's enough to prove that these points are aligned. So look at them. AD and EF, AB and CF, BE and CD. Why are they aligned? It's again a Pascal theorem from one of the hexagons. So we used it 4 times. So we use in this proof of incidence 4 times Pascal's theorem and once one of the implications of Desargues' theorem. All the proofs of all the incidences are of this nature. But you see, how do you find the configuration on which to make the proof? Is not at all obvious. Here there is a whole combinatorics which in all these 95 points and 95 lines makes you extract exactly this piece on which you can do this. How is it possible to invent that? There is a sequel to this article, but I will jump on this. If you are interested, I can send you the beamer. I won't speak on this because there is no much more time. And I want to give you the answer. I wrote to Alex Riba last year asking him how they could find the configurations to which to apply the Desargues' theorem. And he was very nice. He wrote a long email, and I want to show you only one paragraph of that email. He said, for the most part, we used Desargues, as you say, but we found it hard to find the right configurations. In the end, I wrote a computer program, so you see, his specialty computer sciences, that searched for them. Some of you, I'm sure, like very much computer sciences, so you can think, how do you write a computer program which finds, searches for such configurations on which to apply the Desargues' theorem? That allowed us to settle on a very efficient sequence. In 2 pages, we cover what Veronese covered in about 70 pages, with a more roundabout sequence of applications of Desargues. In fact, the idea to use Desargues, you see, comes again from the 19th century. I am amazed that Veronese managed to make sense of all the incidences without a computer. I'd like to know how he kept track of everything. So here is a job of historians of mathematics, to see if at some moment they can find the notebooks on which Veronese worked, to see how could he get an orientation in all these lines and points. So here I jump on Veronese's paper. Also about this, I give you only the idea, is that Veronese paper is the first paper of Veronese. He was very young, and his paper inspired a very important mathematician of Italy, one of the fathers of Italian mathematics, Cremona. And Cremona, in his last paper, because he just became senator, and that killed his mathematical life, he did not have any more time for doing mathematics, well, he said, I have a simpler proof of all the properties proved by Veronese by going to space, and by looking at everything from the viewpoint of space. So again, like conic sections, he has sections of a cone. And here's the clue. How could Cremona find something like this? Is that because more than 10 years before, Cremona had written a long paper about the geometry of cubic surfaces in space. And one of the most famous theorems of algebraic geometry of the 19th century is that if you have a smooth cubic surface in space, it contains exactly 27 lines. And here you see two models of cubics with their lines, either with a surface shown and the lines drawn it, or only the contour here of a piece of a surface and only the lines which are drawn. This was the first complicated configuration of lines to be studied in the 19th century, 27 lines. And in fact, also here you have a very interesting incidences. And for instance, if you look at the group of symmetries, so permutations of the lines which send the configuration in itself, it's a group with several hundreds of thousands of elements. And its internal structure is very rich and it's connected with many other things. And these 27 lines on cubic surfaces were fascinating for mathematicians in those times. A measure of that fascination is that around 1900, 125 years ago, there were already more than 300 research papers on this theme. And Cremona is one of those researchers. But Cremona knew them so well that he had also understood what happens when you deform your surface. We already saw that in that family of cubics in the plane. You do the same. You can deform cubic surfaces in space till they degenerate in some way. And here's a clue for the viewpoint of Cremona, is that here, I don't know if you see that there is a kind of tube inside the surface. And you can, in fact, shrink it till appears locally a conic point, like in the cone of vision. In fact, in that tube pass 12 lines. And when you have that shrinking, those 12 lines will collapse 2 by 2. And at the limit, you will have only 6 lines passing there. So you remove 12 from 27, you remain with 15. So it means that you remain with 15 other lines not passing there. And in fact, this is what says Cremona here. He starts with sia F una superficie di terz'ordine dotata di un punto doppio conico O. And he says that you have to look at that surface from that point. So you start from a cubic surface with a conic point, and you look at it from that. And here he says that there are 6 lines passing through O, and you have altre 15 rete, which means other 15 lines. And he explains that that configuration of lines allows you to understand all the 95 points and 95 lines of Pascal's theorem. And why? What does this have to do with a conic with 6 points on it? Is that if you write the equation of the cubic, taking the origin at the conic point, that being singular means that you do not have terms of degree 1. So in your polynomial of degree 3, you have only a part of degree 2 and a part of degree 3. So the equation of the surface is like this. And now you can look separately at the 2 surfaces here. These being homogeneous polynomials, as Tessier explained to you this morning, they are cones centered at that point. And those cones intersect, in fact, in 6 lines by Bezout's theorem, because here we have degree 2 and degree 3, and the product 2 by 3 is 6. And if you look in perspective at that, you see on the plane at infinity of the space, the quadric cone here is a cone over a conic. And these 6 lines give you 6 points on the conic. This is a relation of Pascal's configuration with the cubic surfaces with a conic point. So you see that you need there a small part of algebra which tells that if you choose carefully the origin, the equation is of this precise shape. And I want to show you also that this shape is very near the trick we did with conics. We had 2 objects, and we make a combination, linear combination of these 2 objects. But here this is done in space. And let me jump on this and say a word only about Pascal in all of this, because I did not explain at all what Pascal did. In fact, Pascal stated his theorem in this page. There is one page, which is from the years 1640. Let us see precisely where. The figure is this one. Do you see a hexagon? The text is this one. I won't let you find a hexagon because there is no hexagon in the statement. The first time Pascal's theorem is stated and illustrated, you see hexagons nowhere. But Pascal was 16. And in fact, with the exception of this paper, there is nothing published which remained from Pascal on Pascal's theorem. So is it a legend? Let us analyze this. First, I want to show you an extract of a paper of history of mathematics by René Taton, who studied very carefully the mathematics of that period. The essay for the conics, of which we still have 2 copies, is in the form of a small poster measuring 35 per 33 centimeters, printed on one side only, and bearing no indication of the printer. This last feature is undoubtedly due to the fact that 50 copies of this poster were printed, intended solely for distribution to Pascal's friends and some of Mersenne correspondents. This very limited distribution explains why this text remained unknown to many geometers of the 17th century. As was common practice at the time, the author's signature is limited to the 2 initials BP, par BP here. This may also be explained by the fact that Pascal considered his essay to be no more than an initial sketch, intended above all to test the reactions that the more extensive study he was preparing would elicit. So we wanted to see just the reaction of the public. Well, afterwards, things are lost. But they were present at the time of Leibniz in 1676. Pascal was died at that moment, had died, sorry. And here is a fragment of a letter to Perrier, who was a husband of a sister of Pascal. And Perrier had sent to Leibniz in Paris the papers of Pascal on the theme of projective geometry, of perspective. And the beginning of the letter of Leibniz is like this. Sir, you have obliged me greatly by sending me the remaining manuscripts of the late Mr. Pascal on conics. For in addition to the marks of your benevolence, this is a style of 17th century. All the letters were like this, which I greatly appreciate. You have given me the means of benefiting by reading the meditations of one of the best minds of the century. I would nevertheless like to have been able to read them with a little more application, but the great number of distractions which do not allow me to dispose of my time entirely have not allowed me to do so. Nowadays, mathematicians would say the same. They have a lot of reports to write and things, and they don't have time. This did not change. Nevertheless, I think I have read them enough to satisfy your request, and to tell you that I have them complete and finished enough to appear before the public. And so that you can judge whether I am speaking with truth, I want to give you an account of the parts of which they are composed and of the way in which I think they can be arranged. And then he said, first part, we must begin with a piece whose inscription is Generatio coni sectionum tangentium et secantium seu projectio periferia tangentium et secantium circuli in quibuscunque oculi plani et tabella positionibus. I don't understand Latin, I read it as a Romanian. So if you know Latin and you say, how is he reading? I know awfully. For this is the foundation of everything else. And only this part remained till now. And this part is a wonderful part in which Pascal says, I am looking at a circle from outside, I draw the rays, and the first theorem, if I take that cone, any plane in space cuts it. You cannot find a plane disjoint from a cone obtained by taking the lines from a point to a circle. Team for you, how you prove it. And Pascal does this with a wonderful language. It's nearly poetry. And then, after having explained the generation of the sections of the cone, made optically by the projection of a circle on a plane which cuts the cone of the rays, that is why I explain you this in this way, because I wanted to be near the spirit of Pascal. He explains, so this is an extract of Leibniz letter. He, Pascal, explains the remarkable properties of a certain figure, composed of 6 straight lines, which he calls a mystical hexagram. I put before these words of hexagramo mystico et conico. It means that he sends back the papers of Pascal to Perrier, but he added something manuscript on them, in particular these words. So that's how we know that this mystical thing comes from Pascal. But we have no idea why he called this mystical. We know that Leibniz saw it written there. And what happened after Leibniz said that this should be published now? All that disappeared. We don't know why it was not published, but it is lost. And here, it's an extract from a paper, so if you get my beamer, everything in blue is clickable. So if you click on it, you arrive to that paper and you can read it. And this is a wonderful paper, how Leibniz read Pascal's geometry. The practice of reading as hybrid hermeneutics in the materiality of Leibniz Pascalian. This is a paper of philosophy of mathematics. Here about how Leibniz, at the end of the 17th century, interpreted the geometry of Pascal. And in particular, the documents of Leibniz were much better conserved. And this is a manuscript, really written by Leibniz, of drawings for Pascal's theorem. And here we see that Leibniz already drew non-convex hexagons. And here is an illustration of a Pascal line. And you see here, hexagramum Pascalianum mysticum, written by Leibniz. So the mystical thing is there. But is this a copy by Leibniz of something already done by Pascal? We have no idea. And happily, we have no drawings by Pascal of these kind of things. So if you want to know more, this is more for you, even for the times of your PhD. Majority of these papers are not for you now, but all the introductions are for you now. You will discover a lot of directions of research. For instance, here, already in 1900, Richmond explained Pascal's all these developments of 95 points and lines, not going to 3-dimensional space, but climbing 1 dimension more, from the viewpoint of 4th-dimensional space. And there he found a wonderful configuration which by projection explained everything. And each paper shows you another perspective of development. So I promised you to show, I did not promise, I told you that there was a drawing of all these things done at the beginning of 19th century. Well, it is this one. In a text by 2 sisters, Anne and Elizabeth Linton, Pascal's mystic hexagram, its history and graphical representation. I hope that this shows you what Cayley meant when he said that he can understand absolutely nothing from this drawing. You see, it's difficult to discover incidences in this drawing. So, for the end, I show you a photo I took in Kyoto last year, which for me, when I saw it, I say, this is a dragon of perspective. You see a circle seen in perspective, and parallel lines seen in perspective, and I hope I convinced you that all this story could develop only because we put things in perspective. So in your life, I wish you, when you think that you have a difficult problem, to try hard to put it in perspective, because in general, this is a way we can progress. Thank you very much for your attention.
Okay, any questions?
I have one such question, maybe a little bit too technical, but what other mysticums can we construct potentially in higher dimensions, which have similar, very, how to say, beautiful group theoretical structure within them?
So I know that there are a lot of papers starting from the 19th century of this kind, but unhappily I did not pursue them. In fact, this is not part of my research. At some moment, I had to choose a subject of a talk in memory of a very good friend and somebody who was very important in my mathematical life, Nicolas Bergeron, and I chose this subject believing he could have appreciated it. And why did I think about this? Because in fact, for several years I directed small group works in second year of university called Mathematical Exploration, in which groups or on average 3 persons were studying a paper and learned how to present pieces of it orally, and also they had to explain in a written way what happens in that paper. So the spirit was to give papers which were concentrated for their age, and they had to expand it till it became readable for second year of university. And one of the papers which attracted me most was this one. So when I was thinking about what could I speak, I was thinking about this subject. And then I began, for preparing my talk, to explore all of this. So everything I told you, and also fragments of history of math, I learned while I prepared the talk. And that's why, not being my specialty, I remember I saw papers which went in this direction, but I don't remember precisely which ones. But I believe you can find elements of answers in this list. So if you are interested, just go and look at these papers, and I am sure in some of them you will find the references which allow you to go in this direction.
Patrick, would you be able to upload this lecture on your website? I think we will do that eventually, but it will take time to upload it on the website of the Institute, and so that students have access to it immediately,
Yeah,
so to speak. Yeah.
But I don't have my website. I was obliged to change my website, and my new website, I don't know very well how to manipulate it. So.
Okay. So if you want, but if somebody wants to see your lecture, they can email you directly.
For the moment, it's better, yes.
Yeah, maybe you can write your email on the whiteboard. Email address, yeah. Yes.
Well, if you allow me one more provocative question, do you think that Kepler knew about the Pascal theorem?
Sorry, can you repeat?
Do you think that Johannes Kepler
Yes.
knew about Pascal theorem?
I have
Because
no idea.
all the orbits of the planets, and not only the planets, but also satellites.
I don't
and
know
asteroids.
if he thought about those conics in visual ways. I think you can, as I explained you can arrive naturally at the statement thinking visually.
Yeah.
But for him, I think
No, he had
that
to
they appear
reconstruct-
differently.
He had to reconstruct the ellipses just by points, but this is projective geometry, because the point on the heavenly sphere, it's actually a line. And
But
so-
as far as I read the historical papers about what Kepler did, he arrived at the idea of ellipses in a very roundabout way and very philosophical. It was not a simple extrapolation from measurements. It was different. But I don't remember this well enough. But one of the reasons of the importance of conic sections is that they have many different definitions. So they can appear visually, but they also appear metrically. And what has to do a section of a cone with taking the sum of distances from a point to two other points? It's a miracle that we reach the same thing. So I don't know even. Why not? Because Kepler thought about many different things. But till now I never saw a testimony of the fact that he could have found Pascal's theorem.
Okay, well, thank you. Very
In any case, it's the same period.
Inspiring
The years
lecture.
1620, 1640, everything takes place there.
Thank you very much.